identity rate change graph, if it truly is the rate change graph, then it has to define what rate change is and its identity. It reveals its identity to you. So based on that, we do a simultaneous analysis. And I'm just going to point to the numbers here. I don't think that's a thing. But so we're going to look for our square values. Here are the 1s, here's the 4, here's the 9, minus 9 and 9, and the 16 is down at the bottom there. Now that translates into this nice little package here that so we're going to identify these geometrical creations, and we're only going to use 2 ADPs that create the rate change out. There can be more, as you saw the 149, but we're only going to use the minimum qualifiers. And what this happens to do is it actually creates these rate change objects, and these are the objects that you are using in physics right now. The first one is integrated when we have the 1 and 1 together. We have an object called the instantaneous, which is at minus the 4 and then minus 4. We have an exponent object that's 4 and 9, which is this here. We have increasing rate change, which is this value, and decreasing rate change, which is that value. And then we have something that's called a field derivative series, which is the 16 and minus 16. Now, the numbers are just place values. They don't really represent anything at this time. However, the flow of that energy gives you these rate change objects. Now, in a dictionary, the Oxford Dictionary, you look up rate change. In physics, you don't even have an idea what this is. In mathematics, they start off with an example about F equals a function, so they really give you an idea. This is a true vision of the different rate change objects you can create in physics. The testing that you do, it's all there. Now, if you don't believe me, let's just take a quick look at how rate change is involved with calculus. Well, it's very simple. Here we have the derivative y entity is the number of horizontal increments. So the derivative of y, which is here, which is y squared is, if we're talking about 5 increments and we're doing about 5, let's say seconds or 5 the total is 25, which would be y squared. We have the 5, which is the base, which is 1, 2, 3, 4, 5 there. And then the horizontal increment counts, which is, of course, the derivative, which is 2n minus 1. In Newtonian, in the way he did the calculus, there's actually more ways to do that. You can eliminate y, you can add y. It just depends on what you're doing. And so, in my technology, and in the, 2 minutes already? I haven't even got, that's the problem with what I have here, is that I have a hard time, I have to explain to you what the technology is, then I have to go to the geometrical physics. All right, what I'm going to do is an analysis. I'm going to select the model, I'm going to perform an analysis, simultaneous analysis count. I'm going to identify the ABPs like we did. Then I'm going to configure the objects and apply rate change and then determine the results. So we said 2y plus 2 is going to give us our geometry. It gives us 4 across that really kind of like works for us. And so now I just identify those objects. I start counting both directions, one positive and one negative, and we come up with our objects, the square up numbers that create straight lines down the graph. Now we draw in our ADPs, which are the values, and well, at the top here, remember we had 1 and 4 crosses, so that creates a double derivative field series, and then we have a regular field series across here. And so those values are qualified. Now what I'm going to do is I'm going to twist. In order to make these two models go together, I'm going to take the standard model and twist it 90 degrees counterclockwise so that the boson region is synonymous with that. And what we're going to do is we're going to go ahead and we're going to calculate our instantaneous rate change right there. And that's the basic rule of it. However, when you talk about rate change mechanics, then you can talk about gravity and all these other things. I can just simply say that gravity, I can simply say that gravity always goes from low to high, right? So I'll take those values and do the same thing. I got here 1 to 4, which is good for the low to high. -4 to -1 is low to high. And -4 to +4 is also low to high. Now what I'm going to take for you is I'm going to also show you that this was in the boson region, right? So now we have these vectors, basically. We already saw the 1 to 4, -1 to -4, but now this -4 to +4 gives us a 0 point here, which could be a break in symmetry that a lot of you guys always talk about. It's involved with the Higgs mechanism. Also in this area, we have these rate change objects. I didn't tell you how we evaluate the integrated rate change object itself, but what it does is that top to bottom, low to high, we evaluate the integrated ones as absolute values. So if we go to low to high on the absolute value here, 1 and 4, anyway, you're looking at the Higgs mechanism as it would. If you took that and you use this, you could probably create the mathematics for it. I created the geometrical points for you. You can also get the leptons and all that stuff by really just adding most of that stuff on there. And, well, this is the analysis of that, is that the GSM creates a perfect structure of the standard model, period. GSM also parallels the standard model operations with RGG mechanics, and it makes a lot of more data available. Critical details were singled out. I didn't have time to point out the half-life, the W boson, the absolute energy, but you can see right here that if this is a photon, because there's an object in there, this would be a W boson with the information here and there as on the standard model. I'm sorry I didn't have time to go through. I have actually a larger one that even points out more stuff. But as a self-affine geometry representation system, rate change graph technology is a new science topic that explores the nature of universal laws. By redefining and repackaging dated modes of analysis, we can extend methodologies with RTGT into 21st century science, the way I see it. Mechanisms to model and perform WYSIWYG solutions, which I did not support, it's not there. No other known geometrical system can create an exact version of the standard model except for RGG's GSM. And rate change provides rich source of data to solve problems and create alternative methods. Thank you. That's any questions? I really did go too fast, and I know it's a little hard because it's really simple, but yet it's very complex at the same time. You can visit my website there. I've got a lot of information out there already. I'm going to be updated in probably another month or so. If you'd like to leave your card here, I can send you my full version of this lecture, and you're going to get a lot more out of it. Thank you very much.